Okay, we're about to talk about some of the reactions that can be done with amines themselves. And the first one we're going to talk about is the formation of diazonium salts. Now, this topic is a little bit of a review from our discussions of aromatic compounds. So I'm going to remind you a little bit about how this, actually works. So first things first, you have to use sodium nitrite in order to make these diazonium compounds. And you do this in the presence of acidic solution because what takes place with nitrite is that you first protonate the nitrite, making nitrous acid in the process, shown right here. But you use plenty excess of HCl, so much so that you don't just protonate nitrite once to make nitrous acid. Nitrous acid is weak, HCl is strong, so HCl basically bullies nitrous acid into becoming a base or acting as a base under these conditions, so that it gets protonated one more time. And that protonation ultimately leads to formation of water, the great living group water. So what happens really is that the oxygen on the opposite end brings electrons in, attacks the nitrogen in the middle, and allows for the second nitrogen oxygen bond here on the right side to be broken. You basically produce water as a byproduct, but you also form this nitrosyl cation, which at the moment is balanced out by a chloride anion. So this nitrosonium ion, excuse me, is the key component to this reaction. All right, so yes, we prepare this thing in situ, and we do it at low temperature, generally speaking. So what I showed you before in the aromatic chapter is that when you have aniline as your component, which truth be told is a primary amine, you basically react aniline with nitrosonium ion. The aniline attacks nitrogen. You break the nitrogen oxygen triple bond. You make it into a double bond. But then you form this intermediate that has a nitrogen with two protons. So one of those protons is removed and reallocated back to the terminal oxygen. That terminal oxygen ultimately, now has a positive charge as a result of that protonation. So basically now you have a second deprotonation taking place back at the original nitrogen. So you remove the second NH bond that it used to have. Those electrons move over to the adjacent nitrogen, and you kick the electrons back to oxygen, forming this neutral intermediate. Now you have also formed HCl in that process, so that goes again to protonate the oxygen that we have here on the terminal position. And when that happens, you have now formed a water leaving group. So the nitrogen on the opposite end brings its electrons towards the middle nitrogen, and then that allows the water leaving group to take off. And this is the full mechanism that we talked about in the past for making diazonium salts. Now, the diazonium salts of aromatic compounds are very reactive. You can basically use that as a means of functionalizing your aromatic compound. You could add fluorine if you want to your component, right? So if you want to produce put a nitro group in there back from a diazonium component, you could do this in the presence of HBF4 and sodium nitrite, excuse me. You could also install halogens like chloro, bromo, or iodo if you use the corresponding copper 1 salt. You could also introduce fluorides if you use HBF4 and you heat up the mixture. You could put a cyano group with copper 1 cyanide. You could put hydroxide with water. You can reinstall a CH bond onto your aromatic using hypophosphorus acid. So basically, we've talked about all of these reactions in the past, but it is a powerful reaction for functionalizing aromatic compounds. Situations, functionalizations that normally would be very, very difficult otherwise to apply. Now, technically speaking, you can make diazonium salts of non-aromatic alkyls, but those molecules are very explosive and very dangerous. So um, very seldomly would chemists actually go out of the way to make those compounds. There's some situations where you do make them, but they're kind of control and kind of exceptions to the rule that tend to stabilize the anion. But we're not going to be talking about those molecules in this class, unfortunately. Um, so yeah, we'll go with the premise that alkyl diazonium salts are just not something you want to make. Now, on the other hand, you can make these things called nitrosoamines. Now, the difference here is that unlike the diazonium salts, where we start with a primary amine to basically go through that entire process of making the diazonium salt, if you instead mix a secondary amine with nitrosonium ion, well, something else happens, and not because the chemistry is completely different, but because of the lack of NH bonds. You only have one here, whereas we had two in the past. So the first thing that happens is the same thing that we saw with the primary amine. You attack your nitrogen, you kick the electrons onto oxygen, and this gives you the following ammonium intermediate. Now, that proton of NH gets removed, right? So the chloride can easily take that proton away, and the electrons move over to nitrogen, and we produce this intermediate. Now, this intermediate here is called a nitrosoamine, and because you no longer have any more NHs, the reaction kind of stalls right at this point. You can't really, you don't have enough protons to produce water as a living group. So even if you protonate this oxygen right now, it's still no water, so it's not going anywhere. So you're literally stuck right at this point, and so you just end right there. So these molecules, the NO2, or excuse me, the NO double bonded moiety, that's called nitroso, and it happens to be bound to an amine, so that's where the name comes from. This is a nitrosoamine. Now, as it turns out, unfortunately, nitrosamines tend to be carcinogenic because they get processed in your system into the azo compounds, like azo compounds, which kind of interact with DNA and cause other problems. So most of them are carcinogenic. And here's the part that's a little bit scary. Although in food you don't have nitrosoamines, you do have sodium nitrite as a preservative, specifically for meat products. So processed meats probably has sodium nitrite, and the meat is gonna have proteins in it, and those proteins have amines. So you could envision that yes, you probably are producing a certain amount of nitrosamines in those systems, and that could ultimately mean trouble for you. Maybe your digestive system, gets messed up over the years. I know that mine has. So yeah, I mean, that might be the cautionary tale for you guys, unfortunately. But yeah, just watch out for sodium nitrite as a preservative, because this is a potential problem. All right, but aside from that, you know, public warning, there are other compounds that are not necessarily as crazy, but then again, there's a limit to this. There are these azo compounds, which basically can be formed from the diazonium salt, the aromatic diazonium salt specifically, if you happen to be forming that diazonium salt in the presence of another aromatic amine. Now, this aromatic amine, or not aromatic amine, excuse me, aromatic compound, what it has to have is a good electron donating group, like this amino group. It could have been an alkoxy group, it could have been phenol, it could have been regular aniline as well. As long as it's a good electron donating group onto this aromatic ring, something very interesting happens. You don't have your typical substitution at the carbon where the N2 fragment is positioned to just undergo a typical substitution. Instead, due to the bulkiness of the two aromatic rings, um, the electron set from the lone pair of nitrogen does move over, kicking away these electrons until at the pair position of the ring that has electron donation, or activation, it attacks, but it doesn't attack the carbon of the nitrosonium ion. It attacks the terminal nitrogen instead. And what that does is it kicks the electrons over to the internal nitrogen, and it forms a compound that looks like this. Now, this is the Meissenheimer complex, of course. So there's one additional step that has to happen, and is the deprotonation, for two reasons. One, not only to remove this proton from the equation, but also to have the electrons go back into the second ring, move about, and rearrange so that now we have aromaticity back into that original ring. So once this happens, and it happens very efficiently, you have a system that is polyconjugated. I didn't say poorly. I said polyconjugated, as in many uh, double bonds in conjugation with each other. So what you find out in real life is that many derivatives of these compounds, so these diazo compounds, and I'm highlighting in red the diazo component, like this one right here, are actually food dyes that we have in many food items. Now this one right here, with the two naphthol moieties and plenty of sulfonic, well, technically sulfonate, sodium sulfonate groups, entirely there for the purpose of solubilizing this organic nonpolar molecule in water. This thing is a really colorful dye, and it's all a result of the polyconjugation that we have in this molecule. So you have this, as you know, this red dye, and that's why this molecule is also referred as to acid red 18. You have other derivatives as well, like this one has um, a 5-member ring with two nitrogens, a pyrosol ring. But the same idea, right? You have your diazo fragment, you have your sulfonates that solubilize things, this entire molecule in water. This one is called yellow 5, and as the name implies, the dye itself is yellow color. And in case you're wondering, these are pictures of the actual dyes, the diazo compound. So this is not a random solid that happens to be red. It's that one. And same thing goes for tartrazine. That is how the actual pure compound looks like. And just to give you one more, one more example, here we have another diazo compound, also rendered soluble in water by having the sulfonate groups present on them. This is called sunset yellow or yellow 6. And yes, it has, in pure form looks more orange, so it's, take it for what it is, right? Once you dissolve it, depending on the dilution, it will probably look yellow, right? But the pure thing, looks more orange to me personally. But yeah, so these food dyes, are used a lot in today's society, but you still kind of want to limit as much as possible your exposure to them, because they can produce some unwanted, results once they interact with DNA and other things. So, for better or for worse, they make beautiful compounds, but you gotta be mindful about the moderation of intake. All right, so with all of that being said, we are done with this lecture. I know there's a few other topics that you might see in your textbook that we haven't quite touched, but we covered the bulk of what I think is important in regards to amine chemistry. And we will definitely touch upon on some of this chemistry again once we start talking about proteins. So stay tuned. But until then, have a good day and catch you in the next lecture series. Bye bye.